Okay, let's finish off chapter 15, folks. Composites and inverses. There are two different notations that we need to know. They both mean the exact same thing. This is a function g followed by a function f. It's a little more obvious, I think. In that notation, we can kind of see that we're going to do g of x, then do f of that, just following like normal order of operations. But that symbol there, that little circle, it's not times. It means following. So that's f following g. There's actually other notations out there in various branches of mathematics, but these are the two that we really need to know for this course. So we have two simple examples down below. If we're given two functions, f of x and g of x, find f of g of x and then find g of f of x. So it's really simple. In each case, we're just putting one function into the other one. You can see how that's happening there. And what is really important to note is that the order definitely matters. Most of the time, f of g is not going to be equal to g of f. It can happen in special cases, but we should not expect that under normal circumstances. We can also apply composite functions to specific values. In this first, we're getting g of f of -1. So in our work, we're putting -1 into f and getting out -11 from there, and then putting -11 into g to get our final answer. Another way that we could have done this is just like in the previous examples, we could have worked out what is g of f of x, and then if we just put -1 in to that, we'll get the same answer of 110. So whichever way you find easier, do it that way. And on the right, we see that we can also compose a function with itself. So we can calculate f of x, or of 0, or whatever. And you can continue that iterative process as many times as you want to. Back in 2014, the IB had a question which involved a very large composite function where we had f composed with itself n times, and you needed to do some other stuff with it. Won't get into that here, but there's no limit to how many functions we can compose or how many times we can compose a particular function with others. When we think about the domain of a composite function, we should look at the final simplified form, but we also need to consider the most inside function that went into it, and consider that as well for the domain. To show you what I mean, if we have these two functions here, f of x equals x squared, and g of x equals the square root of x. If we calculate f of g of x, clearly the square root and the square are going to cancel out, and we're left with just x. Now, what's the domain of y equals x? Well, that would be all real numbers, right? But that is not going to be the domain of this composite function, because we could not have put all real numbers into its first function. G of x is only defined for x greater than or equal to 0, so that ends up being the overall domain for our composite. You can always verify things like this graphically. Here's y equals x. There's our composite function. It lies entirely on top of the original line, except it's only defined for x greater than or equal to 0. Let's look at some more interesting ones. So this is out of the homework set, but I'm going to do it for you here. We have two functions, f and g. First, I just want to note their domains. For f, obviously x could not be equal to -2, and for g, x could not be equal to 1. Now we're going to calculate f of g of x, g of f of x, and g of g of x. So written in black is the work to find f of g of x. We're literally putting this function itself in for each of those x's, and then we're just simplifying. Eventually we get 4x minus 2 over 3x minus 1. You could do similar work to work out g of f of x is 2x plus 5, and g of g of x is just equal to x. So I won't show the work for those, but it's the same idea. Now as for the domains, clearly in letter A, so for f of g of x, clearly x could not be equal to 1/3, because I see that would give me a denominator here of 0. But then we also consider the inner function, which was g, so also x could not be equal to 1. For letter B, g of f of x, when I look at 2x plus 5, that looks like it's defined everywhere, but I got to consider the inside function was f, so x could not be equal to negative 2. And then C, g of x, we're just considering g here, so again, x could not be equal to 1. And before we move on, I just wanted to call your attention to this right here, because a moment ago we saw that the square root of x squared was equal to x. And that should kind of make sense on some level, because squaring and square rooting, those are obviously opposites. They should cancel out. Here, it's not clear why g of g should just give us x out. But we'll come back to that in a few minutes when we get to the next section. And again, we can go to technology to verify. So a lot happening on screen right now, but if I turn off f and g, then I just get f of g. Clearly, it's got a vertical asymptote right where we said it should be. That is at 1/3. But if I look really closely, you know, it certainly looks like it's defined every place else. And I mean, if I keep zooming in here, it's going to always look as though it's defined when x is equal to 1. But if I click on the graph, it'll tell me that it's undefined. Now, I'm bringing up Desmos because I think it's a powerful tool that's quick and easy to use at home while you're playing around with mathematics. Obviously, you can't use this on like a class assessment. Bad news, I don't know of any way to deal with composite functions on the nSpire unless you have a CAS, which we don't have for this course. So for us, we've just got to do the algebra and know what we're doing. Let's do one more. Here I've already worked out f of g and g of f. Those weren't particularly challenging, but now we're going to think about both the domain and the range of those composite functions. For the domain and range of f of g, okay, for the domain, when is that function not defined? Well, for that, we need 1 minus x squared to be greater than or equal to 0, right? Because we can't take the square root of a negative. This is a fairly simple one to work out, but let's just reinforce some ideas from previous videos. I'm going to make a sign diagram. So I'm going to factor the left-hand side. That becomes 1 plus x times 1 minus x. And then I'm going to make a sign diagram to figure out where that's bigger than or equal to 0. Clearly, I've got negative 1 and positive 1. And this is a quadratic, which is opening downwards. So therefore, we're going to have minus plus minus. So where is it greater than or equal to 0? Anywhere from negative 1 to positive 1. We don't need to worry about the inner function here because x squared is defined everywhere. So the domain is simply negative 1 to 1. And if I could do the domain also for g of f, g of x is just 1 minus x. That's clearly defined everywhere, but we need to keep in mind that f of x, the inner function, that's only going to be defined when 1 minus x is greater than or equal to 0, which is equivalent to saying that x is less than or equal to 1. The ranges are going to be a little bit trickier, I think. For f of g, okay, we're taking the square root of some stuff on the inside. But the stuff on the inside was part of a parabola, right? So the smallest value that we could possibly get out of f of g, the smallest value that we could get after we take the square root, is going to also be the smallest value from that portion of the parabola that we're using, which is just from in between those two endpoints. And that smallest value will be at the endpoints. And if we put in negative 1 or 1 into f of g, we'll get 0 out. So we can say for sure that 0 is going to be the lower bound of our range. And that makes sense also because f of g is a square root function. So that shouldn't have any y values less than 0. Now the largest value that we're going to put into that square root, that's going to be at our vertex, which in this case is clearly going to be when x is equal to 0. When I put in x equals 0 into f of g, we get 1 out. So that's going to be the upper bound of our range. We could also work this out with calculus, but most of us don't know that yet, so we won't bother with it. As for g of f, again, that's a line, so that should be defined for all y values, except we've restricted our domain to only look at x values that are less than or equal to 1. For this line, that means that our range is going to be any value greater than or equal to 0. Now we're in section F, which is about inverses. Now I've talked about relations versus functions in the previous video. Now I'll take that one step further, and we're going to define a one-to-one function as being, well, it's a function, which means that every x is matched up with exactly one y, but we can also reverse that and say that every y is matched up with exactly one x. So that's what it means to be one-to-one. A one-to-one function is going to pass the vertical line test. Again, it's a function after all, so it must pass that. But it also passes something called the horizontal line test. Any function that is one-to-one, any function that passes both the vertical and the horizontal line tests, is going to have something called an inverse function, which would denote, it looks like an exponent. It's not an exponent. If it were an exponent, it would mean that we were taking the reciprocal of f of x. But that's absolutely not what this notation means. If I wanted to write the reciprocal of f of x, I would either write 1 over f of x, or what we could do is write f of x and then some brackets all to the power of negative 1. That would be acceptable notation for the reciprocal. Anytime that we see f with a negative 1 right there, it means we're dealing with the inverse. Got to make sure we're clear on that. Okay, so if a function's not one-to-one, we call it many-to-one. It's still a function. Again, a function means that each x value goes to exactly one y value, but a many-to-one function means that many x values go to the same y value. So as an example here, we see x squared. And certainly for any particular y value on that function, except for its vertex, for any other y value, there's going to be two x values, many x values, which are associated with that same y value. This is certainly a many-to-one function. We can see here it fails the horizontal line test. Therefore, this function does not have an inverse function. Now, the book is pretty specific. It always says that a function either has or does not have an inverse function. Could we say that x squared has an inverse, which is plus or minus the square root of x? I think yes. We would just say that that inverse is not a function. So you can see the vocabulary here is a little sloppy. As long as we say the two-word version, then we'll be safe. X squared does not have an inverse function. We can make a new function out of a many-to-one function by restricting its domain, which in this case would mean cutting off the domain here at the vertex, or really any other point to the right of it would do. And that way we're only looking at a portion of the graph which is one-to-one. So if we say that we have a function which is x squared, but only on the domain x greater than or equal to 0, whatever, or less than or equal to 0, or again, you could say greater than or equal to 1. Lots of options. Point is, if we restrict the domain appropriately, then the new function is one-to-one, and it will have an inverse function. What do we need to know about inverses? Okay, first of all, the notation already covered that. Second, an inverse function needs to satisfy the vertical line test. Talked about that already. I mean, it's a function, so it's got to do that. That means that its original function, not the inverse, but the original one had to pass both the vertical and the horizontal. Third, this is important, the inverse function's graph is going to be the reflection of the original graph over the line y equals x. And fourth, it's going to satisfy this property that the function and its inverse should cancel out. No matter what order we apply them in, they're always going to cancel because they're inverses. So f of f inverse and f inverse of f, they're both equal to x. So the function y equals x is kind of special because it is its own inverse. But it's not the only function out there that is its own inverse. One example might be y equals 1 over x. And we actually saw another more complicated example just a few minutes ago with that example where we had g of x equals x. So if we flip back, that was a function which was its own inverse. But how could we find an inverse? And therefore, how else could we identify at a glance whether a function was its own inverse? Well, it's really simple. We just exchange x and y and then solve for y. So in this example, which has a typo in it, by the way, this should read f of x equals 5x plus 2. We'd find its inverse by exchanging x and y and then solving for y. Here's how I would do it, because they're using this notation with the colon and stuff. I find that to be obnoxious. So what I would write is, if y is equal to 5x plus 2, then x is equal to 5y plus 2, and then we solve this equation for y, and clearly we're going to get y equals x minus 2 divided by 5. Some things to notice, just algebraically, we have inverse functions here. So in the original, it was times 5, and in the inverse, it's divided by 5. In the original, it was plus 2, and in the inverse, it's minus 2. And those are also happening in the opposite order. So in the original, we multiplied, then added, and in the inverse, we're subtracting and then dividing. Anyway, we notice that when we graph both of these, here's our original, here's our inverse. They certainly are reflected over the line y equals x. And because we're exchanging x and y, that means that the domain and the range are also going to flip. So the domain of the original is the range of the inverse. The range of the original is the domain of the inverse. In this example, since they were linear functions, the domain and range are obviously both all real numbers. But that's an important fact to remember, as often it's easier to work out algebraically what the domain is of a function than what the range is. So if you're asked to find the range of a particular function, sometimes it's easier to work out its inverse and then find the domain of that.
So I want to share with you kind of a silly trick to help you graph inverse functions while you're still getting used to the process. And it relies on the fact that when we go from a function to its inverse, we have to switch x and y. But more specifically, we need to switch positive x with positive y and negative x with negative y. I'll show you what I mean with this piece of cellophane. Now you'll notice that my axes are labeled as positive x, positive y, and negative y. And I have our friend, the function y equals x squared, as long as x is greater than or equal to 0. I want to graph its inverse. Now I want to switch the positive x and y axes. And I can't do that, for example, just by rotating this way. I've got positive x is pointing up now, that's great, but positive y is pointing to the left. That's no good. Likewise, I can't just rotate this direction. Now y is going in the right direction, but x is flipped around. And neither of those look like what the inverse of x squared should look like. You might also notice that the line y equals x has been rotated in both of these, and that's no good either. What I can do, however, is flip it vertically and then rotate it. And now you'll see that I've got x plus pointing up and y plus pointing right. And that's also exactly what the inverse function should look like. That looks just like y equals the square root of x. Now the best part is you don't need to do this on cellophane. You can actually do this on paper during class, even during an exam, as long as no one's cheating off of you. If you've got your function drawn on a piece of paper, all you need to do is flip it and rotate it and then hold it up to the light. In fact, you can probably see it already through this paper, but just in case you can't, so there's no excuse for you to not be able to visualize an inverse function based on the original. And eventually you'll be able to do all this just in your mind, but if you're uncomfortable with the process for now, this is a trick you can use to help get you there.
One final thing I need to point out, in your work, if you're asked to find an inverse of a function, or if you're trying to label something on a graph or whatever, this is another reason why we love f of x notation for functions. It wouldn't be helpful, and nor would it be correct within the context of these problems to simply write y equals 5x plus 2 and y equals x minus 2 over 5. If you're given that a function is named f of x, then your inverse must be named f inverse of x. So when you're doing the work to find the inverse function, don't stop at y equals x minus 2 over 5. Go one step further and write f inverse of x equals x minus 2 over 5. The IB has specifically mentioned in mark schemes in the past that you should lose points if you leave out the f inverse notation. Now I'm going to do one more because I really like part C. That really jumped out at me here. So there's the two answers for A and B. Those should be pretty easy for you to work out if you're interested in them. But now I want to look at C. So here's your work for that. we can see that I've done the left-hand side separately from the right-hand side. This is a show that question, so I wouldn't want to do anything where I'm crossing over the equal sign, because if I write them out as an equation and then cross over the equal sign, then I am assuming that they're equal from the beginning, whereas the problem is telling me to show that they are actually equal. So I simplify both sides separately, and I get the same answer. And so that's kind of mildly interesting that this should happen, but is there something particular about these two functions in this problem that should make this occur? Well, actually, no. This is going to be true no matter what functions we start off with. If we take a composition of inverses, that's going to be equal to an inverse of composites in the opposite order. The proof is actually somewhat complicated, although I'll put a link in the video description if you'd like to see one. I will say this, however. If I put on my socks, and then I put on my shoes, and I want to undo all of that, get back to my bare feet, I've got to take off my shoes and then take off my socks. I enjoyed this quotation when I first came across it, and I think it's a lovely insult to use against your peers who perhaps don't share the same academic pursuits as you. They are but tolerable subhumans. But I must point out, anyone can wear shoes, but truly, they must understand inverses and composition of functions if they want to have any hope of ever going back to their bare feet again.